So the topic for the day is multiplexing in computer networks. What is basically multiplexing? The set of techniques that allows the simultaneous transmission of multiple signals across a single data link is known as the multiplexing. It is done using multiplexer and demultiplexer, as you will see in the next slides. So in a very basic setup, the whole channel is used by a single transmitter to transmit data, and the receiver receives the same data. As you can see here, the channel capacity may not be used to the fullest, which is where multiplexing comes into picture. In case of multiplexing, we assemble the n inputs into a single channel and then transmit this data across to the n number of receivers. Now, how is it possible? Obviously, it is possible by using some hardware. The hardware concerned is the multiplexer known as MUX and the demultiplexer, as you can see in the diagram. The multiplexer combines n input lines in order to generate one output line. So here you can see n number of input lines and one output line, which is carried across one link. So at the receivers end, demultiplexer separates the stream and directs them to their corresponding n lines. So n lines here and n lines here. In between they are carried as a single link. So what basically are the advantages? With the help of multiplexing, more than one signal can be sent easily over a single medium or a link, as you just saw in the previous slide. So this part of the figure shows you a scenario where we have not used any multiplexing. That means this source is sending data to this source is sending data to this destination, and so on. So in case of multiplexing, we assemble the data or the input from various sources, then propagate them along through a single link, and at the receiver's end they are directed to the corresponding receivers. So multiplexing helps in the effective utilization of the bandwidth, because as we discussed earlier, in case of a one-to-one source and destination communication, we may not use the channel capacity to the fullest. So in this case, it is not the case. So what are the various types? So multiplexing, we can have analog multiplexing or digital. In case of analog, we will be discussing FDM and WDM, wavelength. Similarly, in case of digital, we will be seeing the TDM. So here they are. First of all, we will discuss frequency division multiplexing, or in short known as FDM. FDM is an analog technique. So what happens in case of FDM? We have signals having different frequencies are combined in a composite signal and then transmitted on the link. That is, multiplexing is done on the basis of frequencies. Here the transmission path is divided into 3 channels in this example that carry one transmission, and the channel is usually separated by strips of unused bandwidths, which are known as the guard bands, to prevent the signals from overlapping. So you can see we have the n number of inputs or the sources. Then we have used a multiplexer, which has created a common link consisting of various frequencies. At the receiver's end, a demultiplexer would do the opposite of it and would direct the data to the concerned receivers. So another technique is the wavelength division multiplexing, or commonly known as WDM. WDM is another analog technique. Here optical or light signals are transmitted through the optical fiber. Since optical fiber usually is used to transmit data in the form of light or optical signals. So light waves from different sources are combined into a composite light signal, and this signal is transmitted across the channel to the receiver. As you can see from the signals from various sources in the so lambda here represents the wavelengths or the wavelengths of the n inputs. Then they are combined together and propagated along the fiber optic cable to various outputs or the receivers. On the receiver side, the composite light, composite means which was consisting of data or the signals of various wavelengths combined together. So this composite light signal at the receiver end gets broken down into different light waves with the help of dim multiplexer. So here they get dim multiplexed. So combining and splitting the light waves is done with the help of a prism. As you are already familiar with the properties of a prism. So here a prism is used to do the multiplexing at the dim multiplexing part. Similarly, we have another technique that is known as time multiplexing or time division multiplexing, in short called TDM. TDM is a digital technique. So here is the difference. The previous two were the analog techniques. This one is the digital technique. So in this case, the channel is divided on the basis of time, not on the basis of frequency, not on the basis of wavelength. So what does that mean? That means total available time on the channel is divided between different users on the channel. A time interval, which is also known as a time slot and time slice, is allotted to each user on the channel, and it is during this time that the user has to send the data across. So every user has a specific time slot, as you will see in the next slides also, because we are coming up with two variations of the time division multiplexing. So the first one is synchronous time division multiplexing. Here each device is given the same time slot to transmit data or the link, whether or not it has the data to send or receive, right? Each device places data on the link whenever its time slot arrives. Thus the control is given to each device turn by turn, right? Time slots are organized in the form of frames. So here you can see the frames, where each frame consists of one or more time slots. A time interval is allotted to each user on the channel. So this is the frame 1. Frame 1 has a time slot for A, B, C and D. Here supposedly during the time slots of A, B and C, they were able to send the data. So we have received data from A, we have received from B and C and D, as you can see from the inputs. So in case of frame 2, node A or the computer A or the user A or the source A has sent data or has used the time slot to send or receive data. So is the case with B. C has missed out, but its time slot. Here you will have to remember, in fact we already discussed here that the time slot is reserved whether or not some source is sending or receiving data. So you will have this slot blank. That means C hasn't sent or received data, right? Same for D. So D has transmitted data or put the data in the frame. Same way in case of frame 3, only A and D were able to send or receive data. Similarly for frame 4, only A has. So that is why you are seeing here 4 A's, because A is present in all 4 cases, B is present in 2 cases, C is present in only 1 case. So C has used the time slots scarcely. That means only once. Here C is empty, here C is empty, here C is empty, which is kind of a problem with this synchronous time multiplexing, that your time slots would get wasted if there is no data. This is where we take the help of asynchronous time. So in case of asynchronous time division multiplexing, the time slots are allocated dynamically. There are n input lines and m slots, thus always m is less than n. So you can see we have n input lines and we have m slots. M here is 3. Number of frames is 4. Number of frames is 4, but the slots 3. There are 3 slots. Frame 1, check here. Frame 1, you have 3 slots. Frame 2, you have 3 slots, and so on. Each frame mainly contains the address part that is used to identify the source of the input data. Now a point to remember here is that in case of the synchronous time division multiplexing, as you can see here, this slot was allocated to A here, A here, A here. Then this slot was allocated to B, 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 and B. Whether or not they have to send or put the data on the line, that is a secondary question. But the important thing is a frame is allocated to each line. So same for C, 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 and C, and D, and D, and D, and D. But in case of asynchronous time division multiplexing, it is not the case. So here A has put the data, B, C, then D, A, and B, then D, A, and D, again D, which is not the case in case of synchronous TTM. Same for this frame. So this is why we say the time slots are allocated dynamically. That is, time slots are allocated as per the availability of the data on the input lines, right? So each frame mainly contains the address part also. Now the things we just discussed necessitates that since the time these slots are not allocated to a specific node at a particular point of time, it could be data from any of these input lines. This necessitates that we associate an address with the data. So here if we see some data, but we should know this is the data from which input line. Similarly, like this B2, in case of B2 we should know that what is the data and which source it is coming from. That's why it is saying each frame mainly contains the address part that is used to identify the source of the input data. The number of frames in this multiplexing depends upon the statistical analysis of the number of input lines. So here in number of input lines are 4 and the number of frames is also 4. Thank you.